In this online lecture, we're going to look at some additional reactions of organic molecules. You've seen that you can have oxidation and reduction, and what you do is you look at the numbers of hydrogens and oxygens. Well, we're going to add to this hydrolysis and condensation. In condensation, you basically are taking two molecules together to form one by the removal of water. So if you look at these two, this can be any part of an organic molecule, and this can be any part of an organic molecule. What are you doing? You're taking a hydrogen from one molecule and the whole oxygen and hydrogen from the other molecule and removing that. And what does that make? Water. And because you're removing a bond here and removing a bond here, those two then end up being attached where those bonds were removed. In hydrolysis, it's the opposite direction. We're taking a bond that is carbon to oxygen and carbon. We're adding water in, and where we cut right here on one side of the oxygen, if we're cutting away the oxygen, we put a hydroxyl group, and on the oxygen that has been cut away, we put a hydrogen. So condensation is the joining together of two molecules by the removal of water, and hydrolysis actually says what it is. It's water cutting. Lysis means to cut. So we're cutting the molecule with water. Here is an example of ATP going to ADP and ADP going back to ATP. Okay, we see that just examine this part of the molecule stays the same. So just look at this part right here. Okay, we have oxygen, phosphorus, oxygen, another phosphorus, oxygen, then a third phosphorus. Let's look over here. What is it? We see oxygen, phosphorus, oxygen, phosphorus, oxygen. One of the phosphoruses is gone. In fact, it's called phosphate. That's the phosphate right there. What happened? We cut right here, or you could say we cut right here. It doesn't matter. But the way that the red is showing, we cut right here. So that's this portion of the molecule. It's been flipped over. Where the phosphorus lost a bond, you put on a hydroxyl. Where this oxygen lost the phosphorus, you put on a hydrogen. And so we had hydrolysis. Now what happens? They can go back on. They can do condensation. If you take this off and take this off and join where you removed something, then you get this molecule back again. The other type of reaction we have are called addition reactions. In an addition reaction, a double bond undergoes a reaction. Here is a double bond between two carbons. What are we going to do is we're going to take a molecule. Now X may be more than one atom, or Y might be more than one atom, but we're going to take a molecule. We're going to cut the bond here. When we cut the bond here, X goes on one carbon, Y goes on the other. And so we add a molecule across the double bond. This is called an addition reaction. So here's an example. This is hydrogenation. Here we have the double bond is going to add hydrogen across that double bond. It's going to have hydrogen added across it. Now we have to use a catalyst or it doesn't happen. So we either use platinum or palladium. Okay, so this bond is cut. This hydrogen gets attached here. This hydrogen gets attached there. And we go from having unsaturation to having saturation. Here is an example of the hydration, water being added across the double bond. Here is the water that's going to be added across the double bond. Acid is the catalyst. So what do? We cut one of the bonds. we put a hydrogen on one side and hydroxyl on the other. And do note that what happens to this double bond? One of the double bonds is cut, so it gets attached to a hydrogen. This bond is cut, so the hydrogen then gets attached to that carbon. Same thing here. One of the double bonds is cut, hydrogen on one carbon and hydroxyl on the other. And you can see we make an alcohol. We go from an alkene to an alcohol in hydration. So now you go ahead and figure out what is the product of hydrogenation of cyclohexene and 2-butene. Okay, the hydrogenation of an alkene is going to give you an alkane. One of the double bonds is cut, and a hydrogen goes on each of the two carbons in the double bond. That is the product. What about here? Well, here we're not drawing the hydrogens in. There's a double bond, it gets cut. A hydrogen was added here and one here, but because we don't write double bonds in skeletal structures, you don't write it out. We just understand that there are two hydrogens here, and there's only one here, so it added a hydrogen. One hydrogen here, two here, so it added a hydrogen. In hydration, there's a little bit of selection to hydration. If I look at this hydration, you will see there are 3 carbons here. This carbon is different from this carbon in the double bond. This has only 1 hydrogen on it, and this has 2 hydrogens. When we add water across this double bond, the second bond is cut, and we're going to put a hydrogen here and a hydroxyl here. Now you might say, why won't the hydroxyl go here and the hydrogen here? Well, it has to do with the mechanism and what actually goes on in the intermediates. But what we always find is that the hydroxyl ends up being attached to the carbon with more carbons attached. So you see, this carbon has 1, 2 carbons attached. This carbon has only 1 carbon attached. So Markovnikov's rule is, when doing hydration, the hydroxyl goes to the carbon that has more carbons attached. If it's symmetrical, you don't have to worry, you can put it on either. That's what happened here. This is a symmetrical molecule. Well, it's not there. Okay, but that's a symmetrical molecule, so it won't matter if you hydrate this where the hydroxyl goes, and the same with this. All right, you go ahead and try it. Well, the first thing that we do is we see it's symmetrical, so it doesn't matter which carbon we put, which of these 2 carbons that we put the hydroxyl on. So we put a hydrogen on one and a hydroxyl on the other, and the double bond is now a single bond. We're doing the same thing here with this one, but you see that this carbon is identical to this one, so it doesn't matter whether we put it here or here, is identical. Hydrogenation is a very important step in food. If you look at the unsaturated fatty acids in nature, we find that they are almost all cis fatty acids, meaning the double bond is a cis double bond. But the problem is food manufacturers do not like having cis fatty acids in food because they're easily oxidized, and so the shelf life is short. Now, oxidation does not make it unsafe. What happens with oxidation is it gets an off taste, and most people won't eat things that have an off taste, even though it's perfectly healthy. So what food processors do is they want to use either saturated fats or they will want to use something that's called partially hydrogenated fats. So they can saturate them completely, and then it's called saturated fatty acid. Or if they don't use enough hydrogen, you get only a partial reaction, and we get what's called partial hydrogenation. And in the process of only partially hydrogenating the unsaturated fatty acids to saturated fatty acids, the leftover double bonds all become trans double bonds. And these we found are just as unhealthy as a saturated fatty acid. So here's an example. Here is a cis unsaturated fatty acid. You see that this and this are on the same side of the double bond. If I draw a line through this double bond, you see they're all both above. All right, so if we do hydrogenation over a platinum catalyst, some of them are going to add hydrogen across the double bond, and we get this saturated fatty acid. But if they don't use enough hydrogen, there's going to be some double bonds that aren't hydrogenated, and what happens is that the double bonds that do remain are trans. And what we have found is that these trans fatty acids are just as, possibly even more, unhealthy fatty acids to eat. They cause clotting of your arteries around your heart and up in your brain.